Welcome once again to this lecture. We are going to move ahead and study more about vector spaces. Once again, we defined a basic abstract notion of a vector space and then used only aspects of that definition to develop the area more. In the previous lecture, we saw linear combinations, span, subspaces, and how to deal with subspaces, etc. Some various examples, ways of thinking about them, and very importantly, linear dependence, linear independence. What does that mean? All of that we saw with the basic definition. We are going to build further and study about basis and dimension. So this is quite crucial and important notion in a vector space. So let's go ahead with it. Okay. Quick recap, we studied this in the last lecture, particularly linear combinations, A1 V1 plus A2 V2, things like that. Plus then we looked at span. Span of a set of vectors is all possible linear combinations. And then we saw subspace, the most important idea of a subspace, how when you have a subset of a vector space, which itself is closed under addition and multiplication, scalar multiplication, you have a subspace. Right? And then this notion of a linearly independent set of vectors, as in other than the trivial combination which gives you the zero vector, no other combination can give you a zero vector. Okay, so these are important ideas. We did have this question on how to establish linear independence or dependence. We didn't fully answer that question. That's still lurking around. It's not going to go away. We'll eventually see that there are interesting methods to do such things. Okay, so let's proceed. So this slide is quite important. There's lots of detail in it. I'll walk you through one after the other. The first thing we will define is something called a spanning set for a vector space. Okay, so this is an important definition. A set of vectors v1 through vn is said to be a spanning set for the entire vector space if the very obvious sort of definition for a spanning set. What is spanning set? A set that spans the whole space, right? So if you say a spanning set for the vector space, what you mean is if you take the span of these vectors, span of v1, v2 to vn, you should get the entire vector space. No vector should be left out in the span. Okay? If you have a set of vectors like that, then you have a spanning set of vectors. Okay? So look at the definition once again. It's there on the top of the slide. If you have the span of v1 through vn, a set of vectors v1 through vn is called a spanning set if the span of those vectors is the entire vector space. So we saw some examples of this before. I will quickly give you other examples, etc. Okay. So basically what it means is every vector in the vector space can be written as a linear combination of vectors from the spanning set. Right. So that's what it means. It's sort of a restatement of the definition in some sense. Okay. So we can give you examples. And in these examples, I'll start denoting vectors instead of the column vector description that we had before, a big matrix-like thing occupying a lot of space. We'll reduce space and write vectors as rows. Okay, so just imagine that these are actually columns if you want to. Okay, so these for simplicity, I'll write it like that. So you notice here for F2 and F3, it's very easy to come up with a spanning set, right? So for F2, 1 0 0 1 is a spanning set. F3 1 0 0 0 1 0 0 0 1 is a spanning set, but remember these are not the only spanning sets, right? So for F2 we saw other examples, right? So you remember in one of the earlier examples we saw that 1, 2, 2, 5 is also a spanning set, right? So those two vectors end up spanning the entire R2, for instance, right? So there are many spanning sets, but it's easy to come up with one spanning set. Quite quickly you can come up with one spanning set. In general, for Fn, I can come up with a spanning set. 1 followed by zeros, 0, 1 followed by zeros, like that, right? The ith vector will have 1 in the ith position and 0 elsewhere. Okay, so that is the spanning set. These type of spanning sets have a name. These are called, so these are sort of standard in some sense, right? Like I mentioned, there are many other spanning sets. But these particular type of spanning sets where you have just ones and zeros, ith position has 1, everything else has 0, that kind of thing is called a standard sort of spanning set. Okay, that's nice to know. Now we come to the important definition of a finite dimensional vector space. Okay, a vector space V, we will call it finite dimensional if it has a finite spanning set. Okay? If a finite number of vectors span the whole vector space, that vector space itself is supposed to be finite dimensional. Okay? We haven't yet told you what dimension is. I will say that in some time. Dimension is something we have not yet defined, but we will define finite dimensional in this form. If it has a finite spanning set, then the vector space is finite dimensional. So clearly f power n, fn, this website where this vector space with n coordinates written one below the other or one after the other in a row, that vector space is clearly finite dimensional because there are n vectors which completely span the space. Okay, so that's a nice enough example for us to have. There are also other things which are finite dimensional. You see the polynomials of degree less than or equal to 1, that's finite dimensional. I've given you a spanning set there. The matrices, m cross n matrices, they are also finite dimensional. You can come up with a matrix once again in the ijth position it's 1, everywhere else it's 0, right? If you take all such matrices together, they will clearly span the set of all matrices. So that is also finite dimensional. But here's an example. Out of all the examples we saw, the last example was these functions from real numbers to real numbers, right? This ends up not being finite dimensional. Okay, there is no finite spanning set. Think about how to prove it. The proof is sort of already in this page. You can go back and look at the polynomials and argue that how, if you have all type of functions, then your polynomial need not be finite degree, right? And when you have polynomials of any degree, clearly you're not going to have a finite set of vectors which span the whole space, right? So you can prove this in that fashion. So already we have seen out of the examples, some of them, most of them seem like are finite dimensional, but at least there is immediately there's one example which is not finite dimensional. Okay, and this Fn is a special sort of finite dimensional vector space. It turns out, we'll see later, that any finite dimensional vector space has to look like f power n. Okay, so that's like sort of like it's a canonical standard sort of finite dimensional vector space. Okay, so this finite dimensional vector space is very important. For the rest of this course, we will focus only on finite dimensional vector spaces. Most of the results we have will be for finite dimensional vector spaces. Okay, so these are very important. Okay, so now we slowly start taking steps towards technical aspects of this course. We have already seen mostly definitions, and here is a lemma which talks about linear dependence in vector spaces. And this is sort of a technical lemma. What do I mean by technical lemma? It's a lemma that's useful to prove other things. By itself, it will look like a simple result. Okay, you may not look at it, you might look at it, read it and think, okay, what's the big deal in this result? So it's a very fair reaction. A lot of people will have that reaction, but it's very useful. Okay, so you'll see in various other results, I will end up, at least in this class, using this lemma again and again and again, and it's a very powerful result to have. So many results in many areas in mathematics develop like that. There'll be like one basic lemma, technical sounding lemma, which by itself may not mean much, but eventually you'll see it's so useful in proving results. Okay, so let me read out what this linear dependence lemma is. Okay, supposing you have a set of vectors v1 through vm, and supposing they are linearly dependent. Okay, so it's a linearly dependent list of vectors in some vector space V. So it turns out, whenever you have a set of linearly dependent vectors, there is an index j, okay, such that Vj, that is the jth vector, belongs to the span of all the vectors that came before it. What does that mean? Vj can be written as a linear combination of v1 through vj minus 1. Okay, so let me write that down, that aspect of it. So vj equals, for that particular j, vj is some a1 v1 plus so on till aj minus 1 vj minus 1. Okay, so there exists a1 a2 to aj minus 1 such that this is true. Okay, so that's the linear dependence lemma. Of course, you have the sort of a bizarre situation if j ends up being 1. What is the meaning of j being 1? v1 is a linear combination of nothing, right? So nothing comes below it. Before it, that we have to interpret as v1 being 0. Okay, so we'll sort of do a trivial definition for that. So quite often in mathematics this will also happen. You'll write a result and then there will be this trivial corner case for which you have to make an artificial definition. Okay, so that always happens. So in this case there is this trivial case that if suppose v1 ends up being 0, right, everything else is linearly independent and v1 ends up being 0, then the j here is actually 1. Okay, and then when j is 1 you have to account for it as 0. So this special case we will just deal with it in that fashion. Okay. Not only that, that's the first result. It says v1 to vm. If somebody claims they have a linearly independent set of vectors and they order it like that, they say first vector, second vector, third vector, like that, you can find one jth vector which will be a linear combination of the j minus 1 before it. Okay, that's the result. It's a very simple sounding result. You will see in the proof that it's also a very simple thing to prove. It's not very complicated, but it's very powerful. You can use it in so many interesting ways, and you'll see when I use it to prove other results, you'll see that it's very powerful. Okay. Now look at the next part. Okay, next part is actually quite easy to visualize, right? So once you have Vj being a linear combination of V1 to Vj minus 1, if you drop Vj from your list of vectors, the overall span remains the same. Yeah, that's not very difficult to imagine, right? Span is all possible linear combination. If you already know Vj is a linear combination of V1 through Vj minus 1, you might as well drop it from the list. You know that you can generate Vj if you want and everything else is okay, all right? So that's the second part of the result. We will prove the first part alone. It's not very hard to prove. You'll see the proof is quite easy. I will write down the proof in the whiteboard. Okay. So notice v1, v2, vm are linearly dependent, right? Okay, this has been given to you. That implies what? There exists a1, a2, am, not all 0. Okay, so that's what the linear dependence means, such that a1 v1 plus a2 v2. Okay, so where do they all belong? They all belong to the field F, right? a2 v2 plus so on till am vm equals 0. By the way, I don't keep repeating it in every lecture, but we will always assume we are dealing with a vector space V over a field F, and this F is usually R or C, but in these kind of results it can be anything. Okay, so that's the way to think about it. Okay, so now among this A1 through AM, there will be a maximum index element which is not 0. Okay, I will let J be that value. Okay, so let J be the maximum index such that Aj is not equal to 0. Okay, there has to be a number like that. After all, there are only A1 to AM. Okay, maybe AM is non-zero. Okay, if AM is non-zero, J will be equal to M. Now, if AM is 0, you go to the next one before it, AM minus 1. Okay, and see if M minus 1 is non-zero. If it is not 0, then J will become M minus 1. If that is also 0, you go to M minus 2 like that. Okay, so from the right or from the largest possible index, you keep coming down till you hit the first non-zero guy. You know that will always happen, right? Because at least one of them is not non-zero, so you will hit that, and that one becomes your index J. Okay, so now what happens? So now once you write it like this, so that will imply Aj Vj plus Aj minus 1 Vj minus 1 plus so on till A1 V1 equals 0. Why is that? Because see, once you say J is the maximum index such that Aj is not equal to 0, Aj plus 1 equals so on till Am equals 0, right? So in this summation, all of them will disappear, and Aj is not equal to 0, so I can multiply by 1 by Aj. Okay, since Aj is not equal to 0, I can multiply by 1 by Aj. I will get Vj equals, I will move everything to the other side, minus Aj inverse Aj minus 1 Vj minus 1 plus so on till I should put minus here, Vj minus 1 minus so on till minus Aj inverse A1 V1, okay, and we are done. Okay, so this implies Vj is in the span of V1, V2, Vj minus 1. Okay. So, like I said, the proof itself is really simple, it is easy to write down, you just look at it and argue that there should be a largest possible index, and then after that it should be less. Okay. So, it is a very easy argument. So, we see that this is true. Okay. So, this innocent sort of looking result in some sense is actually very useful to derive very non-trivial results about vector spaces and linear independence, dependence, basis, dimension, etc. So, when I actually prove it, you will see it, but this is a result that is good to know. Okay. If you have a linearly dependent list, there is one element which is going to be a linear combination of everything below it, before it. Okay. There is always something like that. Okay. Alright, let us move on. This is linear dependence lemma. I will use it again and again and again. Please remember that. Okay. Linear dependence lemma. Okay. Alright. So, now we have defined different types of vectors. Okay. A list of vectors satisfies different types of properties. Two important properties we have defined so far. One is the linearly independent property. You can have a list of vectors and you can say they are linearly independent. Another property we defined just about a little while ago in this lecture is this spanning set property. You have a list of vectors and it ends up being a spanning set for the whole vector space. Excuse me. What does it mean to say spanning set? Every vector in the vector space is a linear combination of vectors from the spanning set. Okay. So, you have two different types of sets. One says it is linearly independent, no linear combination, no non-trivial linear combination can give you a 0. Another is a spanning set. Every vector is a linear combination of this. Now, it turns out the size of these two sets are related in some way. Okay. There is an ordering in the size, and that is the result here. This result is very important. In a finite dimensional vector space V, the size of any linearly independent set has to be lesser than or equal to the size of any spanning set. Okay. So, on the face of it, maybe some of you are surprised by this result. Why should the spanning set have a connection with the linearly independent? The linear dependence lemma is what will show you the connection, but we will come to that soon enough. When you see the proof, you will understand. But this is a powerful result to know. Okay. If you have a spanning set, okay, it will have a certain size, there will be a certain number of elements in it, because it is a finite dimensional vector space, there will be a spanning set, right. Any number of vectors more than the number of vectors in the spanning set have to be linearly dependent, right. So, that is what is nice about this result. Look at the example for F3 there. Okay, F3 means you have a spanning set with 3 vectors, isn't it? F3, let me write it down. F3 equals span of 1 0 0, 0 1 0 and 0 0 1, isn't it? Alright. So, we know that there is a spanning set for F3 with just 3 vectors. So, if I give you a set of vectors, set of 4 vectors, right, then they cannot be linearly independent. Why is that? Because if they were linearly independent, it would violate this result that you have, right. The size of a linearly independent set has to be lesser than or equal to the size of any spanning set. I have a spanning set of size 3, which means the maximum number of linearly independent vectors in F3 has to be only 3. Okay. So, look at the vectors here. You might think about linear combinations that result in non-trivial linear combinations that result in 0. Maybe you can try to find it, but ahead of time I know that there has to exist a non-trivial linear combination giving you 0, just because I have 4 vectors and I have a spanning set of size 3. Okay. So, that is what is nice about it. Same thing you can push, right. So, for instance, if you have F10, right, F10, you can argue that any set of 9 vectors will not be a spanning set. Why is that? Think about that. Okay. If you take the standard set of F10, right, 1 0 0 0 0 1 0 0 0 0 1 like that, that is a linearly independent set, isn't it? You can show it is a linearly independent set. So, which means any spanning set should have at least 10 vectors. So, you cannot have a spanning set with 9 vectors for F10. Okay. So, these are the nice results that one can show once you have this result. In fact, look at the final exercise. It's a nice exercise for you. You have to show that in a finite dimensional vector space, every subspace is also finite dimensional. Okay, think about why that has to be true, right? Every subspace should also be finite dimensional. As in, if you have a vector space with a finite spanning set, okay, then every subspace also has a finite spanning set. Okay, you can prove that using this result. Think about how you would prove it. Okay, so it's not too difficult to think about the proof, but it's important to write it down carefully. Okay, so it's a nice little challenge to do this result. Okay, so that's an exercise for you. I mean, you have to try it, see if you can think of a proof for that. But what I'll do in this lecture is to show you a proof of this result. Okay, so it's a slightly complicated proof. If you have not seen too many of these abstract proofs before, it might be a little bit confusing, but stay with me. Try and see if you can follow the proof. It's a very nice, elegant argument. It uses the linear dependence lemma very strongly. Okay, so let me write down a proof for this. Okay, so let's say u1, u2, um is a linearly independent set. Okay, and let's say v1, v2, vm, vn is a spanning set. Okay, so we need to show what m is less than or equal to n. This is our goal, isn't it? That's what we want to show. Okay, so what we will do is this following sort of trick. Okay, I will consider this list u1, v1, v2, vn. Okay, so this is a list of vectors. It's got u1 and then it has v1 to vn. Is that clear? Is that okay? Hopefully that's clear. Okay, what type of set is this? My claim is this is linearly dependent. Okay, all right, so think about why this is linearly dependent. Why is that? Because v1 to vn is a spanning set. Okay, so u1 can definitely be written as a linear combination of v1 through vn, right? u1 is also a vector in the same vector space and v1 through vn spans the entire vector space. So u1 can be written as a linear combination of v1 through vn, and that makes it a linearly dependent set. So now by linear dependence lemma, there exists J such that Vj is a belongs to the span of u1, v1, vj minus 1. Okay. So now remember, u1 belongs to a linearly independent set. u1 cannot be 0 by itself, right? So this linear dependence lemma, if you use, there has to be a vj which is a linear combination of these things. Okay. So what I will do is I will drop the vj from the list. Okay, and I know my span is still remains the same. So I will have this nice result that u1, v1, v2, so on till vj minus 1, vj plus 1, vn is a spanning set, right? Okay. Is that okay? Hopefully you saw the argument here. I can drop the vj and I can still have the same span, isn't it? Okay. So now I start with a spanning set, and what will I do? I will add U2 now to this list. Okay. So let's take U2, U1, V1, V2, Vj minus 1, Vj plus 1, Vn. This is linearly dependent. Okay, the same argument as before. Okay, you have a spanning set. If you have a spanning set, if you add another vector to it, you will definitely get a linearly dependent set. Okay. Now you use linear dependence lemma. Okay. Again, there has to exist a j such that, or maybe I will use j1, such that Vj1 belongs to the span of vectors before it. Why is that? Okay, linear dependence lemma says J1 has to be like that, but then remember U2, U1 are linearly independent. So U1 cannot be in the span of U2, right? So U2 came in, but U1 cannot be in the span of U2 because U1, U2 are linearly independent. So if when you use the linear dependence lemma, I know that there is a J, there is a vector which is in the span of all the vectors before it, but that vector has to be the V, right? It cannot be from the U's, right? So this J1 has to be from among the V's. So what do? You drop J1 also. Drop J1 and add U3. Okay. So like that you keep proceeding. Okay, you drop J1, you will have a spanning set. You add U3, you will get a linearly dependent set. You use the linear dependence lemma. It cannot give you any vector in the U's because U's are linearly independent. It has to give you a V. Okay, and then you drop that, add a U, add a U, add a U. You keep on doing that. In every step, you dropped a V and added a U. You dropped a V and added a U. And by the linear independence lemma, you can keep on going till you exhaust all the U's. Okay. Okay, continue till UM. Okay. Now what did I do in every step? There were a total of m steps, right? In the first step, I dropped Vj and added U1. In the second step, I added U2 and dropped Vj1. And in the third step, I added U3 and dropped another V. Every time when I added a U, I dropped a V. Okay? Without dropping a V, I did not add a U. So what does that mean? Right? And finally, I was able to do it all the way up to Um. So that implies M is less than or equal to N. Okay. Think about that once again. It was a slightly maybe complicated set of sequence. So there is a stepwise way in which we are proceeding. In every step, we are adding a U and dropping a V. Okay, adding a U, dropping a V, adding a U, dropping a V, and I'm able to go up to all the way up to M, which means in the spanning set there must be at least M vectors. Otherwise, I would have gotten stuck somewhere. Okay, and since I did not get stuck, there is no chance for me to get stuck. I can keep on adding U's and dropping V's. The number of vectors M has to be less than or equal to number of vectors M. Okay, so this wonderful little proof which uses the linear dependence lemma and the argument like adding the U's in the left, okay, and then saying that a vector has to be a linear combination of everything before it. Okay, and that's the nice little argument that comes out, and you see that the number of linearly independent vectors has to be upper bounded by the number of vectors in the spanning set. Okay, a nice little proof. If you have not seen these kind of proofs before, it's probably very interesting and maybe a bit mysterious, but this is a very nice proof to show how the size of a linearly independent set has to be upper bounded by the size of a spanning set. Okay, so this is what I mean when I say a very innocent looking lemma which says something very obvious can be used in a non-trivial way to get a very nice result which helps you come up with a lot of nice ideas. Okay, so why don't you try this this exercise? It's a nice exercise. Think about how you will show that in a finite dimensional vector space, every subspace is also finite dimensional. Okay, so it's a very interesting little argument. You may have to use some careful, nice argument to show that there will be a spanning set for the subspace, or Okay, you can start with some interesting ideas like that. Okay, so that's the idea. Okay, so anyway, if we will discuss during one of our regular meetings how to do such proofs. Okay, this leads us to the next definition of basis. Basis is a very important idea in linear algebra. So we defined a spanning set for the vector V, vector space V. We also had this notion of a linearly independent set in vector spaces V, and there was a relationship between these two. Now a basis for a vector space is going to sort of be both a spanning set and a linearly independent set. Okay, so that's the basic idea behind a basis. Okay, so that's the definition in a box for you. A basis of a vector space V is a set of vectors that has two properties. The span of that set has to be equal to V, and the vectors themselves have to be linearly independent. Okay, so if you find a set of vectors like that they're linearly independent and they span V, then that's called a basis. It's a special set of vectors in a vector space V. Okay, so I've given you some examples right below that. There's the standard basis, the standard spanning set that we gave before in FN, that's called the standard basis. But there are many other interesting bases. Okay, in F2 for instance, 1, 2, 2, 3, F2 1, 2, 2, 3 is a basis. But in F2 1, 2, 2, 3, 3, 4 is not a basis. Okay, why is that? Okay, so this is not a basis. Why? Because it's linearly dependent. Okay, so the set will span the whole F2. Okay, spanning condition is satisfied, but the linear dependence is linear independence is violated. Okay, it's not linearly independent anymore. What about this one, 1, 2, 3 and 2, 3, 4 in F3? Okay, so it's not a basis, it's linearly independent, but it does not span F3. Okay, so think about how you can prove it. Okay, you can find, how do you show that a set of vectors do not span F3? You have to find a vector which is not a linear combination of 1, 2, 3 and 2, 3, 4. Okay, so take that as an exercise. Try to find a vector which is not a linear combination of 1, 2, 3 and 2, 3, 4. Okay, so you can do that. Okay. So now what's interesting about a basis is this unique basis representation. Okay, so this is really interesting and important. So once you have a basis, it turns out if you take any vector, okay, a basis is a spanning set. So if you take any vector, you can write it as a linear combination of the vectors in the basis, right? What is unique about a basis is you can write it only in one way. Okay, so if you take any vector and if you express it as a linear combination of vectors in the basis, it is possible to do it uniquely. Okay, as in you can have only one possible linear combination that will give you the vector V. If you do another linear combination, you will get another vector. Okay, but for one particular vector, you will have only one linear combination which gives you. So this gives rise to this vector representation of a list of coordinates representation for a vector. Okay, so if you have any vector, you take a basis from a finite dimensional vector space, you take a basis, okay, and then you write the vector as a linear combination of the vectors in the basis. So now you take the coefficients of those linear combination, list them out as coordinates, you get a coordinate system for the vector space. Okay, so this is the idea behind this unique basis representation. It's very important. So for instance, down below I've given a couple of examples. If you take the basis 1, 0, 0, 1 and you look at the vector 3, 5, you can clearly write it as 3 into 1, 0 plus 5 into 0, 1. You can also take the other basis 1, 2, 2, 3 and the same 3, 5 can be written as 1 into 1, 2 plus 1 into 2, 3. So you see that for the same vector 3, 5, if you change the basis, you get a different coordinate representation. Okay, so this is an important thing to keep in mind. So you have any number of bases. So if you think of the 2D plane and you think of a vector, you have to think of the vector as being the same, and as you keep changing the basis, the vector's coordinates may change, but the vector itself remains the same. So this picture of a vector independent of the basis is something very important. Usually all vectors are described in the standard basis. So once you describe the vector in a standard basis, the vector itself becomes the same. And if you change the basis, the vector remains the same, the coordinates may change. Okay, so something important to think about. And as you change basis, the coordinates can change for a vector, but given a coordinate system, given a basis, the coordinates get fixed. Okay, so that's what's very important. Okay, so we'll see more and more about basis and a lot of properties for basis, and lots of interesting things as we go along. Okay, so here are 3-4 results already coming out for basis. Okay, the first result. Okay, I'm not going to write the proof in detail. You can see the textbook for a detailed proof. I'll just give you a motivation for where it comes from. The first result for basis is every spanning set can be reduced to a basis. So now remember, if I give you a spanning set, already one of the requirements for basis is fulfilled, right? For basis there are two requirements. It has to be a spanning set, it has to be linearly independent. Once I give you a spanning set, one requirement, there's a tick mark, right? So it's already a spanning set. Now only thing I have to make sure it could be linearly dependent. The vectors in the spanning set could be linearly dependent. Now what can I do? I bring in my linear dependence lemma. If the vectors are linearly dependent, use linear dependence lemma to find a Vj which is in the span of the previous guys. You throw it out. Span remains the same. So spanning set property is retained, and then again you check if it's linearly independent. If it is not linearly independent, use the linear dependence lemma to throw away one vector. Okay. So algorithmically how you do it is something we'll see later, but at least from a technique point of view, from a theory point of view, it's clear that if somebody gives you a spanning set, you can reduce it down to a linearly independent set. Once you get a linearly independent set with the same span as the original set, you have a basis. Okay, so every spanning set can be reduced to a basis. Okay, that's the idea. So the next result is very interesting. So once you know, so is there a basis, right? Is it guaranteed that every vector space should have a basis? Okay, I told you there should be a spanning set, there should be a linearly independent set. Will there always be, for any vector space, will there always be a basis? It turns out if the vector is finite dimensional, it will have a basis. Why is that? It's very easy to see, just use the previous result. You know, a finite dimensional vector space has a finite spanning set. Every spanning set can be reduced to a basis, so you will have a basis. Okay, so every finite dimensional vector space has a basis. Okay. And the next result is also interesting. Every linearly independent set can be extended to a basis. What is this extension? Okay, so somebody gives you a linearly independent set. Okay, you take the entire spanning set for the vector space, add it to this set. Okay, you will get a big set of vectors, your linearly independent set and the entire spanning set. Now you start using the linear dependence lemma, one after the other. You throw away vectors from the spanning set till you get, right, a linearly independent set which is a spanning set. It's also a basis. It's also linearly independent, right? So that becomes a basis. All right. So that's the argument for it. You can write it down in a very careful way. So just like this is very similar to the previous proof that I wrote down. I don't want to write down a clear proof once again. If you have a linearly independent set, you can append the entire spanning set to it, okay, right, and then or any other basis to it, and then use the linear dependence lemma. But you know, since you started with a linearly independent set, the first few things will not really show up in your linear dependence lemma. It will show up only afterwards. So only the new spanning set that you added will get chopped down till you get to a linearly independent set, and that one becomes a basis. And it had your original independent set as part of it. Okay, so maybe in your exercises and assignments we'll give you some questions for doing this. Okay, the final result is what's most important. Remember, a basis is both a spanning set and a linearly independent set. Okay, what do I know about size of a linearly independent set? It has to be less than or equal to spanning set. Okay, but suppose now you have two bases. Okay, somebody gives you two different sets which are both bases for the same vector space. Okay, each one is a linearly independent set, each one is a spanning set. So the first size has to be less than or equal to second size, and the second size should also be less than or equal to the first size. So if you have two numbers, both have to be less than or equal to each other. What is the only way it can happen? Both have to be equal to each other, and that's done. Okay. So the last result is very, very interesting. Any basis, any two basis set of vectors has to have the same number of vectors. It cannot be different. If you have a vector space, a finite dimensional vector space, you cannot have a basis with 10 elements and another basis with 12 elements. Okay, it violates the basic conditions that need to be satisfied. So any two bases have the same number of vectors. Okay, So interesting, isn't it? How do you start with some abstract notion of vectors, define some basic rules, and define more things, interesting things, and finally you end up with very nice sounding results such as this. Okay, so this is the power of abstraction. All these results hold for any finite dimensional vector space. Okay, so that's the nice thing about proving these kind of results. Okay, so next we come to dimension. So we saw that any two bases have the same length. Okay, this leads us to the definition of dimension. The dimension of a finite dimensional vector space is the length of any basis. Okay, so this number is very important, and we'll have a notation for it. We will call it dim, next to that v. Okay, so anything I write like that becomes dimension of the vector space v. Okay, so that notation is important. So we can see some examples here. It's easy to write down. Dimension of f power n. Okay, the standard vector space is actually n. You can come up with a basis with n vectors. And dimension of polynomials of degree less than or equal to n is actually n plus 1, right? So if you say polynomial degree less than or equal to n, the basis has n plus 1 vectors, 1x, x squared all the way till x power n. Okay. What about m cross n matrices? The dimension is m times n. Okay, the basis has mn elements. Okay. So just like vector space has a dimension, the subspace also has a dimension. What is subspace? Subspace is nothing but a vector space itself, right? It's a smaller vector space which is living inside a larger vector space, right? So it's also a vector space. So since we also had a result, I gave that to you as an exercise. If the bigger vector space is also finite dimensional, then any subspace is also finite dimensional. It's very intuitive, it's easy to see, but you can write down a rigorous proof also. Okay, so it has a basis also, and dimension of U is the dimension of the subspace. So okay, so for subspaces also we'll define the same notion of dimension. Okay, so the notation will be the same. So if you have a vector space V, its dimension is dimension V. A subspace of V also, we will use the same notation. Okay, dimension of U is the dimension for that. Okay. Okay, so here are a few results on the dimension. First result is, if U is a subspace of V, dimension of U is less than or equal to dimension of V. Okay, so it's sort of obvious in some sense, but you can prove it using the result that size of a linearly independent set has to be less than or equal to size of a spanning set. Okay. The next thing is, a set of linearly independent vectors of size dimension V is a basis for V. Okay. Notice this interesting thing. Once you know the dimension of a vector space, any linearly independent set of size equal to dimension of V, okay, will automatically become a basis. What does that mean? It can span the whole set. Okay. So in F3, if I take 3 linearly independent vectors, I have a basis. It also spans the whole set. Okay, right? So how do you prove this result? You take your set of linearly independent vectors of size dimension V, then append the entire spanning set to it, and you use the linear independence lemma, reduce, extend it to a basis. Of course, it can be extended to a basis. Once you extended it to a basis, the size has to be dimension V. Anyway, originally you started with dimension V. Those are the only vectors that will be left. Okay, so it's a very clean way to rigorously prove this result, that if you know the dimension of the vector space V, right, you just take linearly independent set of size dimension V, you have a basis automatically. It will automatically span the whole space. It cannot leave any vector out. Okay, nice result, isn't it? Same thing about a spanning set. If you have a spanning set of size dimension V, that will also be a basis. If a set of vectors of size equal to dimension V, what do I mean by size? The number of vectors is equal to dimension of V, and it spans the whole space. So in F3, for instance, if you have 3 vectors which can span the whole space, they have to be linearly independent. So they become a basis. How do you do that? Again, you use the same thing. You take the spanning set and reduce it to a basis. Okay. Originally you started with dimension of V. When you reduce to a basis, you will also have dimension of V, which means nothing got reduced. It has to be linearly independent. Okay. So these are all interesting small ways in which you use previous results to build on the existing things and get more and more interesting results, right? So this is how a lot of abstract mathematics proceeds. You start with the basic definition, then you have some lemmas, you prove some basic result, and then you use it more, figure out more ways of using it to get more and more non-trivial result. Okay, so notice how these results are becoming more and more non-trivial. In any vector space, if you have a linearly independent set of size equal to dimension, it's already a spanning set. If you have a spanning set of size equal to dimension, it has to be linearly independent also. Okay, so nice results to know. Okay. Okay, so here are 3 problems. I'm not going to solve them for you in this lecture, but please try them. It's very important to get your understanding of everything right. So here are 3 subspaces that I've defined for F3 and for F5. I've given various conditions. You can check that these are subspaces. I want you to find the basis for these subspaces. Okay, so how do you find the basis for the subspace? Think about the conditions you need, right? How do you find a basis for a subspace? It has to be linearly independent, it has to span. So you have to check both. Come up with a list of vectors, right, which will be linearly independent, which will also span the whole space. Okay, so take up these problems, try them, we'll discuss them when we have a chance to meet live. Okay, thank you very much.